Good morning and good afternoon to everyone. I welcome you all for this webinar episode number 2. We can start the webinar now. So I request all the attendees, if you have any queries or feedback from your side, so please drop it in the Q&A section, okay? So Sudarshan, you can take over.
Yeah, thanks, Brian. Very good morning and good afternoon to everyone. On behalf of DEP team, I would like to extend my warm welcome to all the participants joining us today. Thank you for taking your time to be part of this webinar. Today's session is focused on Meshworks and AI Works, the complete platform overview. Before we get into this topic, let me take a minute and introduce DEP. DEP is a global engineering solution company with over 25 years of experience in helping organizations to accelerate their products development and engineering innovations. Our business is built on 4 key pillars: engineering consulting. DEP provides CAE, validation, and engineering service to global customers. Product development. DEP also supports customers from concept to its prototype. And we have also a talent acquisition team. DEP helps customers to scale their engineering capabilities. And finally, our bread and butter, DEP Meshworks and AI Works. Both are our proprietary CAE platform that enables the automation built to accelerate optimization in the concept level of model. To brief more about DEP, about the engineering consulting, we have been pioneer in working with more than 2 decades with most of our OEMs and with most of the tier 1, especially on the turnkey of CAE based activities. So DEP has successfully worked in many activities, especially from building from its concept till the proto. We have been working with different vertical, from building an EV two-wheeler or creating IC engines or on the drones. We have the end-to-end capabilities. And as I mentioned, talent acquisition is one of the key strengths for DEP in supporting most of the OEMs and its tier 1s companies. We provide a pool of engineers with various domains, starting from CAD, CAE, and even MBSE kind of solutions. I would let my teammate Arun to talk more about the Meshworks and the AI Works platform much more in detail. Today, DEP operates with a global team of 600 plus engineers and domain experts, with more than 60% holding master's degree, enabling us to deep dive the technical expertise across the industries. We have presence in 13 plus countries and have successfully supported 500 plus customers worldwide, including the leading OEMs, tier 1, and different manufacturing sectors. These are some of the potential customers with whom we have been working for a few decades. I'll hand over the stage to Arun. Arun, the stage is yours.
Yeah, thank you, Darshan. Let me share my screen. Hello, all. Greetings to you all. So, thank you for joining this session. So, in this session, I'll just do a quick recap of the topics which we had discussed in the episode 1. Then I'll provide a introduction to Simulate AI, which will cover the key capabilities of our AI Works platform and also some of the use cases, followed by the live demonstrations of our case studies. Okay, with that being said, so in our episode 1, we had discussed about our one of the software platforms, that is DEP Meshworks, which is an integrated CAE platform for pre and post processing that has some advanced capabilities as well. Let me reiterate through that. So we have a nice meshing and model assembly features, which will really cut down your turnaround time, be it tria meshing or a quad meshing or hexa meshing. So all type of meshing and all type of connections you can do with ease. And we have this reduced order modeling capability, which will reduce your solving runtime let's say, if you take a crash example, the major physics of the problem lies on the front side if it is a frontal crash or a frontal ODB. So the rear portion you can convert into a mass representation. So without compromising the physics, you can reduce the solver runtime in a great extent. Or if it is a natural problem, you can quickly convert a BAW into a beam and super-element representation, which can give you 10x time reduction in terms of natural time. Or if it is an abacus type of problem where you need to simulate these kind of nonlinear simulations. So we have this automated submodeling capability, so which will nicely submodel a hotspot region like this, and you can run it very, very fast. So let's say this entire assembly is taking around 20 hours for the solver as a solver runtime. So this submodel will take only 2 hours. And better yet, you can get a proper correlation on the stress as well. And also, you can quickly link it with our parametric engine capability, where you can nicely create parameters, as you can see, to improve your design or conducting some design exploration. And once you do the solving, then we have our post-processing capability with which you can do all kind of post-processing like contour viewing, querying, measuring, and so on. In addition to that, we have this 3D HTML report, we have this generated generation report, which will provide you a tool presentation or PowerPoint like presentation or report, PowerPoint like any higher management can review the model in a 3D mode. Any higher management can zoom in, zoom out, and visualize the contours. It will give you a better visualization options as you can see on the screen. It's actually a 3D embedded model visualization options as you can see on the screen. If you are into, if you like to do some AML case study, and you might have hundreds of models, and extracting the results from each of these designs would be a tedious task. So we have this robotic results processing capability where you simply record the results extraction for one subsystem or assembly or one design, and then the same can be replicated robotically for the remaining designs. So no manual intervene is needed over there. It will robotically go over all the designs within that folder, and it will extract the results and place it in a folder structure within your workstation. So once you do post-process, you may be interested in improving the design. So for which our library of parameters will assist you. So as I mentioned, we have a library of parameters with which one can maximize their design space in order to optimize their design. So in the early stages of design, you might be interested in creating some global parameters. So as you see on the screen, so here I have created a global shape change parameter for changing its width, and here the wing length, and so on. So you may be interested in doing all these kind of global shape change parameters. Similarly, if you take an automotive, so if you like to do some design of experiments or design exploration, you can create all these kind of parameters with ease. So only minimal intervene is needed, and the learning curve is also very minimal. Or if you like to add some topological features, say you would like to add some tetribs or a shell rib, or if you want to add some features like holes, slots, or even a weld parameter. So all these can be done irrespective of a mesh, whatever you have it with you. Whether it is a 2D mesh or a 3D mesh, you can create all these kind of topological parameters as well. Or if you want to add some new bill of material based on the topology optimization study you have done. So we have tools called ConceptWorks, so which will assist you creating a member or any new bill of material without the use of a CAD. So over here you can see from the concept A, where we have identified the load path, we have created this concept B without the use of CAD. Directly on FE level, you can create all these kind of bill of materials using our ConceptWorks technology. Or if you want to add any bows and ribs like this, you can quickly add. Or if you want to create some support members and joints, so all these you can create with a minimal user intervene. So once you have the data ready, or if you already have the enough data for your subsequent AML study, so you might be interested in understanding the cause versus effect or how these data is changing with across each other. So imagine you have hundreds of design, how each design is changing. So that you may be interested in understanding the same. So we have this data analysis module, which we discussed in detail in our last episode, which is like a unique voxelated approach, which will help you track the variation across all your input data or also on your output data. Not only that, it will also give you a statistical variation where you can visualize the mean, median, or any standard deviation across hundreds of designs. So let me walk you through this example. So I have an automotive model. So where if I just cycle through, you can see all the shape variations across hundreds of designs, as you can see. So you can quickly get these kind of useful information with our data analysis tool. And better yet, it will also provide you in a very statistical manner. So if you observe this blue region, across these 100 designs, there is no variation or shape change or any change within this blue region. All the shape changes are happening on the front side and rear side of the vehicle. These kind of useful information and the cause versus effect study, this useful data analysis tool will provide you. With that, let me deep dive into today's topic, that is AI works simulate AI. So as you know from our last episode, we have four distinct modules within AI works. So first is simulate AI, features AI, geom AI, and agentic AI. So in this session, we will cover more on simulate AI, and the remaining will be covered in the subsequent episodes. So let me go to the simulate AI. So the simulate AI in itself is a workflow, as you can observe over here. The first workflow would be the obviously CAE data generation. So you would require a lot of data for doing the training. So as we have seen in our earlier discussions, we have our nice parameterization capability or concept modeling capability, morphing, reduced order modeling capability, and automatic extraction of results through our advanced post processing. So all these functionalities will assist you in generating the required CAE data generator for the subsequent AML study. So now that we have we are ready with the input data, the input designs. So what could be our output responses that we can train? So the output responses could be a scalar value like a drag coefficient, or it could be a vector value like a force versus displacement or acceleration versus time and so on. Or the output response could be a field response as well. Sorry, the field response like a pressure contour or a displacement contour as well. Or it could be actual time history where you can visualize the actual animation of your problem. So the output data could be all these format. It could be a scalar or a vector or even a field or time history. So you can take all your input data along with these output data, which will directly go into the training module of AI works. So when it comes to training, so this is our training module in a nutshell. So you have CAE results in the format of ODB, OP2, D3 plot as such. And these could be in the form of scalar, vector, or a field, or time history, or even a matrix form as well. So all these CAE simulation data will then be automatically converted into a AI works readable format, which we call as MW plot. It will be automatically converted into an MW plot file. So you do not worry about the simulation results format. So we will supply this MW plot file into our AML training architect, which will the outcome of this training would be a family of AML models. So this is a more pictorial representation of previous slide. So I have a different input model along with the output data, let's say the drag coefficient, which will platform, and out the predictive AML model and the generative AI model. So this one we will talk about in the episode 3. So here we will cover more about the predictive AML model. So we have all these neural network models like CNN, GNN, or GCN as such, or even PIN, which most of the competitions have, but how we are differentiating with all these. So let's say this is the neuron layers, pooling layers, or other contents to form layers of different neural networks. And we have unique architectures for solving different class of problems. So by that I mean, so for example, you have a mildly nonlinear problem, or moderately nonlinear problem, or a highly nonlinear problem. So we have separate or distinct architectures for solving all these kind of problem. So for one architecture for solving mildly nonlinear, one architecture for solving highly nonlinear as such. So we have unique architectures for solving different class of problems, and we also have the physics laws calculation as well. So we also embed the physics laws. For example, if it is a CFD load case, we will use the Rand's equation or a Navier-Stokes equation. If it is a durability, we will use the residual equations. So the PDE equations that governs the problem will be kept inside this architecture as well. We will calculate that physics laws as well. So why physics is important? Okay, this is the vector of a highly nonlinear problem. So the right-hand side depicts the nonlinear problems trend line without the use of pin. The blue one is the actual simulated vector or the values. The red one is the predicted vector without the pin. So you can see some variation in the trend line, whereas with pin, you can see the close correlation between the original, that is the actual physics simulated, and the pin predicted trend line. As you can see, a close correlation in the trend line with the pin architectures. Similarly, so this is a plate with a whole problem may appear simple, but it is a difficult problem to solve. So we have this original MW plot, that is original results over here, and you can see with pin and without pin, the difference between with pin, without pin for the stress contour. You can see close correlation once we have pin in picture. Similarly, you can see this example as well. You can see a close correlation with the pin being introduced. This is another example. So that's why the pin is very much important during the for the architecture to predict with very much high accuracy. Not only the physics laws will be captured, the problem physics. So each problem will have a separate physics. So we will capture those as well. For example, if it is a local deformation, the predetermined zone which will be influenced, we will capture it precisely. So all these problem physics as well as the physics laws will be captured with our architecture. And we will provide this equivalent scorer as well. So where you will see all your input designs or all your input designs in a unified voxelated format, which is in blue color. And you have this yellow color is a new incoming design. So once you have that new incoming design, so you can see it is well within the design space that you have trained for. So you will get a predicted value along with the higher equivalent scorer, as you can see over here. And if it is completely out of bound, you will get a direction. However, it will produce a lower equivalent score, as you can see for the green design. Okay, it means that okay, it has not included, no such design has been included in the training phase. You better do the physics simulation, the actual physics simulation, and then you maybe include that data into our adaptive training platform, so that if there is any new incoming design coming after this, we will predict it properly. Okay. So this is the GUI of AI Works. So this is the user experience that you can receive from our AI Works platform, where you can create multiple projects and multiple iterations. You can create sets for the influenced zone. You can generate the training data, you can visualize, you can consolidate all those, and you can do model training by tweaking some hyperparameters as such. So once you are done with the training, so the next workflow would be predicting it. Okay. So as you know, the simulate AI will be used to create surrogate models to replace or to reduce the repeated iterations through the solvers, the actual solvers. So you can, once you build some AI surrogate model, so which will then replace your Nastran or a Dyna or an Abacus. So which will further reduce your design iterations to a great extent. So once you are done with the training, you can bring in any new design and you can bring the trained file. It could be in PT file format or HY file format as such, and just simply click on predict. So it's going to predict a CD as a scalar, or it's going to predict a pressure contour like a field. It's going to predict a time mysteries as well. So whatever you have trained for, it's going to predict that. And we have integrated this auto parameterization module as well. So where you can create parameters, the shape change parameters with minimal user inputs. For example, if you take a drag coefficient problem, so these are all the major shapes which can influence greatly the drag coefficient value. So we have a auto parametric capability which will nicely create all these parameters with a couple of inputs. Okay. So once you create all these parameters with ease, you can then link it with our optimizer. Okay. So you can link it with our optimizer where you can either choose the fast solver, whatever we have built using our training portal, you can use that, which will produce the performance in a minute of time, or you have the liberty to make use of the actual physics solvers as well. That is Abacus or a Dyna also you can invoke, or you can do combination solving as well. So if a problem is going to take 20 hours, for that you can make use of a surrogate model which will produce the results in a quick time. Or if something, some problem which will be solved by the actual solver, let's consider the Nastran. It's going to produce the results within 15-20 minutes. So you can give the Nastran as a solver. So you can couple both the fast solvers as well as the physics-based solvers within our optimization module. So this is one such case study where we have predicted the drag coefficient of this model as a 0.257. Then we have created a lot of parameters, as you can see over here: spoiler height, the angle, the top side width, bottom side width as such. And we linked with our optimizer, the constraint, the objective being reducing the drag coefficient, and it has ran. And the optimizer designs drag coefficient is around 0.232. From 0.257, it has reduced to, the drag coefficient has been improved to 0.232, okay, using the AI-based surrogate model. Let me quickly present some of the case studies. So we have been engaging with different customers across industries, whether it is automotive, aerospace, heavy equipment, or biomedical, or even manufacturing. We have been engaging with multiple customer across industries, and with that, I would like to present some of our internal case studies. So let me start with the full vehicle aerodynamics prediction. So here, yeah. So here we have a different vehicle configuration, and each starting from sedan to SUV to a pickup truck as such. So each of these designs, we have created a lot of parameters. So as you can observe in this design, so we have created a lot of parameters, and we have the drag coefficient for each design. So then, along with all these input design, along with its respective drag coefficient, we had trained using our AI Works platform. So before that, the drag coefficient variation is all the way from 0.29 to 0.35. As you can see, it is well spread across values. So we have trained it, all these design. We have trained all these designs, and while once we are done with this training, we have brought some unseen data, as you can see over here, which were not included in the training, and we have predicted with our surrogate model whatever we have achieved during our after our training, and you can see a close correlation between the simulated value and the predicted value. So you can see the percentage error is less than 1%, as you can see, and you can also see the values as a vector trend line. We are able to achieve this much accuracy, and of course we have validated with R2 score and whatnot. Not only the scalar, we have also predicted the contour, the field responses as well, and we have compared against the actual physics simulated results, and we were able to achieve closer correlation even in the field responses. So of course we will demonstrate all this in a couple of minutes. So the next case study is on the low speed impact of a bumper assembly. So here we have multiple designs, as you can see over here, with a lot of shape as well as thickness variations. While the design is changing, you can also observe the respective center deflection, the peak force are also changing. So we had taken this data along with the output data, and we had trained it for predicting the deflection time history, the peak displacement and peak force, and also the manufacturability parameters like thickness variation and plastic strain. So we have built this AI surrogate model to predict all this, and we were able to achieve a close correlation on this as well, as you can see. Okay. This is the left hand side is the actual physics solved time history or the contour. The right hand side is the predicted output. You can see the close correlation between those two. And this is the thickness variation for the formability applications. You can very well train your model to predict the formability criteria, and you can very well understand where the thickening is happening or where the thinning is happening, and also where the strain is more. So these useful insights it will provide you. And we had also created some parameters all the way from shape parameters, gauge and material parameters. And we linked with our optimizer, and you are seeing the graph that was given by the optimizer. It has generated multiple designs until the optimized design has been arrived. Okay. So over here we have arrived at the optimized design. This is another case, use cases where we have considered 100+ aircraft data, where we have varied wing sweep angle or dihedral angle or the rear horizontal wing sweep angle and so on to predict the lift over drag ratio. So these are all the shape changes that we have considered, and we have predicted with a proper accuracy, with more than 95% accuracy, as you can see. The error percentage is less than 5%. So by the way, these are all unseen data which were not included in the training. So, and this is another case study with respect to NVH performance prediction. So where we have created multiple shape parameters like this, and we have trained the model to predict its NVH performance. And of course, we were able to achieve more than 95% correlation with this NVH case study as well, where we have predicted the frequency as well as the mode shape. And we have compared against the actual Nastran simulation, as you can see. Finally, so we have built an AI surrogate model for a steering wheel assembly to predict its normal modes and frequency, the bending performance, the impact performance, and not only we are going to predict, and we are going to consider all this, and we are going to arrive at an optimized design as well. Okay. So this is the workflow which we have followed. We took all the input and output data. We have trained using our AIWorks platform. We have validated with our with the unseen data, and we have predicted and compared against the actual simulation data, and then we have optimized using the AI surrogate model in order to arrive at the new design, which is the optimized one. So as you can see, this is the baseline design, and we have improved the natural frequency, and the stiffness has also been maintained similar to the baseline, while there is a minimal reduction in the mass. So we were able to achieve this optimized design as well. So with that, I would request Jaswant to showcase the demonstrations of all these use cases. Jaswant, over
Thank
to
you,
you.
Arun. Yeah, thank you, Arun. Thank you. Let me share my screen. So, very good afternoon and good morning for the people joining from all over the world. So, first demo, what we are going to see is on the track prediction. This is a library of data that we used for training. And if you focus here at the rear portion, as I walk you through each design, the drag coefficient is varying while the design is changing. So we have used this set of data to build a AI surrogate model, which when a new design or a unseen data brought in, it will predict the drag coefficient for that. So we have used 55 designs as such. Let's see. This is a new data, a similar camera model, and it is of different dimensions. Now, what I'm going to do is within this panel, I have to specify a AI trained model, that is our surrogate model, which will predict the drag coefficient and provide an output directory, which will where the MW plot that Arun mentioned in his PPT will be dumped. So let me go ahead and select the files. Selecting the surrogate model and providing a meta file which will contains the data for prediction and specifying output directory. Let's say this is my output directory where the files need to be dumped, MW plot files. Selecting the folder and simply say predict. Now with my laptop as the workstation, it will start running the surrogate model and it will run through the new designs that we brought in and it will start predicting the drag coefficient for that. In a matter of a minute, the process will be done. Hope you guys can see the value over here, or else I'll just change the value. You see the CD value that is predicted is 0.277. And if the user has to do some design change and improve, like predict what is the new CD value, that is also done within the same panel. All user has to do is simply get into design change, and with our morphing technology, we can do a design change on the fly. Let's say my intention is to decrease this hood height. I'll simply select the required nodes that I need to modify. And then I will simply add in a deformation zone. I'm defining the design space within which the changes will be affected. So I'm simply selecting the set of nodes here. You can see. And then I'm saying auto find fixed nodes. Behind this, there won't be any change. Now I've created my morph set. I'll simply get into transform, translate, and I'll be selecting the control nodes. And in y direction, I'll be decreasing the height. The model is in meters, so let me go ahead and provide the values accordingly. So my aim is to decrease the height by 50 mm. I've done that, accept it, return, and say simply update mesh, return, and all I need to do is click on predict once again. Now again the surrogate model will start doing its task. According to the new design changes that has been done, it will predict the CD and display it in the screen. we can see from 0.277, it went down to 0.273. So this is the experience you will get with Meshworks AI. Not only that, as Arun alluded nicely in his presentation, if you have a target CD, all you have to do is provide the target here, let's say 2.323. And if I click on optimize, based on the parameters specified by the user, it will start taking consideration of the parameters defined, and it will use the surrogate model for solving, and it will meet this design target. Now I'm not doing it since it will take a couple of hours to complete it, where the couple of days task can be brought down to hours. So this is one advantage of our surrogate plus parameterization technology. Yes. And moving ahead, what we saw now is a CFD problem. Moving ahead, let's say I have a bumper problem like this. This is a crash related, and it's a LS diagram. So as I toggle through the models, we can see the design changes happening at the center. Let me zoom in here. And the peak force and central deflection is also changing according. So with this set of designs, we have trained a surrogate model, which will predict the time history for the bumper. So when I brought in a new bumper like this, all I have to do is select the surrogate model. So let me go ahead and select it. If you can see, I have a library of surrogate models. So one is for a CFD problem, one is for if you brought in a different car and like different geometry of a car, you want to predict the CFD and stiffness. And now I'm going for a bumper, which is a crash. So all I need to do is click on predict. Now it will start writing that MW plot once again, and it will also display the peak deflection and sectional forces. So we can see the peak force is 25.92 and center deflection is 172.63. So let me change the color. You can see the values. Now let's say I want to plot the time history. How I can do? Let's get into a post-processing window. I'll simply call the model. So this is a Dyna file. So I'll import the model, then select this MW plot and say import. Now, how we'll use a D3 plot or a FEM33 plot? We can actually visualize the changes happening to the model for each time step. So give it a minute, it will be imported. Yes. Now the model has been imported. I'll go ahead and plot the contour. We need displacement in X. So I'll simply say contour and I'll get into animation and change it to transient. Simply say play. In a matter of seconds, we not only predicted the peak force and the center deflection, we also have a time history with us, which will work as an actual solver and provide the data. From hours of task, we have brought down to seconds. So now what we have done is predicted the time history. And if I want to do some design variations and improve the model, so we can create a parameters like this. I've created simple parameters. You can see I've created almost 13 parameters here. Let me go ahead and review some of the parameters. So for example, one is this width change. So as I toggle to, we can see the width of the center region is increasing and decreasing. Let's say I want to increase the height. Let me hide this set. Yes, you can see we're changing the height as well. Now let us go ahead and review one more problem, center bead. So I want to change the center part of the profile. You can see the center bead, it is changing according to the design. Not only that, let's say if you want to do a thickness problem, let's say if you want to change the thickness of the bumper, we can create a parameter for that from which the minimum and maximum range can be provided, and we can generate a number of designs out of this. Not only thickness, we can also do a material parameter as well. So we can create the material and material name and go ahead and parameter them. So with this, let me go ahead and show an example where we will create for a bumper model, we'll test the formability at the same time with the elastic strain as well. So this is a fresh window. As we can see, there is nothing in here. What I'm going to do, I'm simply going to create a project. I've already defined the working directory and project name. All I need to do is simply create it. Now what I'll do, I'll get into define design variables where I'll bring in a model where the parameters are all set. Sorry, let me do it once again. It's in a wrong folder. So let's go to bumper formability. So this is the where I want to select, and I want to give number 06 as my project name. Create. Now I'll go to define design variables where I have defined a min max and design parameterized file. So what I'll do, I'll bring in this min max design. So you can see with change and height change, these are the designs I have parameterized, and this is the minimum and maximum value. And when I say define design variable, the model will be loaded according to the parameters that I have defined here. We can visualize it here. So these are the two parameters. Now in a single stretch, I need to predict two output variables. One is the formability, thickness problem, and plastic strain. For that, I'll go to AML response generator where I'll select the design and bring in PT file. This is another surrogate model. First one, let us bring in the manufacturability problem. And I want to extract the maximum thickness and let's say run. Now this design file that I have selected and the PT file that I have selected will work hand in hand, and it will suggest to me these are the responses that can be generated from the PT file. And user can select the responses over here. And it will also highlight the calculation method based on which the responses are generated. And we can always select them here and simply say, you can see displacement x, y, z, and thickness scalar. So I don't need the displacements. I simply need element thickness scalar alone. And it is following GNN, graph neural network. And if I say generate output response, the response is generated. Similarly, I have to generate one more output response, that is the plastic strain. So in the interest of time, I've already generated the response. Now all I need to do is simply say solve. Now parallelly, Meshworks A will work hand in hand and solve the bumper for one thickness problem and two plastic strain. So it is running the surrogate models accordingly, and in a matter of seconds, it will provide us with the contour, which we can visually verify and determine if the model is meeting our standards. It is running now. Give it a minute. Again, all this is happening within my workstation. So you can use any of the workstation to build this surrogate model, and it can be populated within your organization, and anyone with Meshworks can utilize that surrogate model and predict it. So like this. So we can see one is element thickness, another one is plastic strain. So let me go ahead and contour this. So thickness scalar, say contour. Done. And let's edit the legend as well. Similarly for the plastic strain, let me go ahead and contour it. If you could see here, it has predicted that maximum plastic strain is in the region over here. So we can see for formability problem, we can see the thickness range varying. This is the maximum thickness range where it's varying over here. This is another user experience where we have or used our surrogate model to solve two problems in one single click. Now let's say we have a problem like here. I want to predict the modes and frequencies for this model. All I have to do is select the AI trained model. So let me go ahead and select them. Provide output directory. So this output directory can be provided anywhere and with any name I need. And simply say predict. Again, the surrogate model will run through and predict the modes and frequencies for the aircraft model we have in the screen. So it has predicted, and we can simply go ahead and apply the contour, get into animation and see what's the how the model is behaving. Okay, let me go ahead and increase the scale factor since this is a whole model. Yeah. With a few clicks in a matter of seconds, we have predicted the modes for this model. Let me go ahead and conclude with one final demo. And this is another aircraft where I am going to predict the lift over drag. I've already brought in the surrogate model and provided the output direct the MW. All I need to do is simply say predict. So it will use the surrogate model and scan through the STL data. And as we progress through, we can see we are using different type of solver models, like one is Nastran model. One is STL, anything. You can bring in any data. It can be a Nasdaq template, LS-DYNA template, or Abacus template. You can simply use them. And as nicely pointed out by Arun, we will generate MW plot from those data, and we'll use that for training. And for creating parameters as well, you don't have to worry. It can be a solver data or FE data in our LS-DYNA. You simply bring in the FE data. We can go ahead and create the parameters. We can see the leftover drag predicted is 13.55. Now I can go ahead and do design change and repredict it, or I can go ahead and optimize it as well. So this is, yeah, I think with this, I would like to hand over the stage to Arun. Yeah, Arun, over to you.
Thank you.